Hello everyone and welcome to lesson 10 of the Beginner CFD series. In this video, we will look at the natural convection in a square cavity, a classical benchmark problem used for testing and validating CFD codes. Natural convection, also called buoyancy-driven flow, occurs when fluid motion is generated by temperature differences within the fluid itself. Here, we will analyze a two-dimensional buoyancy-driven flow of air inside a square cavity. The cavity has vertical side walls that are differentially heated, meaning one wall is cold and the opposite wall is hot. Let's look at the model and the boundary conditions. The geometry is a square enclosure with each side having a length of 0.07 meters. We consider air as a Boussinesq fluid, which means that the density variation are small and only important in the buoyancy terms of the momentum equation. As shown in this figure, the left wall is kept cold at the temperature of 0 degrees Celsius. The right wall is kept hot as a temperature of 25.2 degree. Both the top and the bottom walls are adiabatic, meaning the heat flux is 0, as you can see here. All the walls have no slip condition, which means the velocity is 0. This setup corresponds to a Rayleigh number of 1e6, which is within the Laminar natural convection region. The mesh for this problem was generated using ANSYS Meshing to accurately capture both the velocity and the thermal boundary layers near the wall. A finer mesh was applied close to all boundaries. The final mesh consists of 35 by 35 quad elements, which provides sufficient resolution for this case. Here you can see this picture as an example of our geometry. So now, as other previous sessions, we can start with the workbench. So I will open a workbench and then drag and drop Flow Fluent into the project schematic here. Then I will save this project and I will call it as natural convection in a square cavity. Save the project. And also I will save this part of the project name. The geometry is very simple. I just click on the geometry, change the type to 2D, and then double click to open the SpaceClaim. Okay, so I can start in the SpaceClaim now. First of all, I will define the plane. Select the plane, XY plane, and then use the plan view. Then I have a normal view on this one. I'm going to use meter unit, so I will go to the file and then SpaceClaim options and then change the unit to the meter. I will just click on the unit here and then change the length unit to meter at the end of this list and press on OK. So I can start to create a sketch. I will use the rectangular, select the origin point of this plane, and then I will just type 0.07. Use the tab key, as you know. I will go to the next dimension here, again 0.07 meter, and press enter. So I have a square here, and then click on the end sketch editing. So I will have a surface here for this part, and then I will go to the groups to define the boundary condition. So I will select left side, use Ctrl G, as you know, to define the name selection. I will call it as left. I will do the same for the right wall. Click here on this edge, Ctrl G, and then call it as right. The same procedure for bottom and top. Use Ctrl G. I will call it as bottom, and then finally I will select the top edges. Use Ctrl G or use the name selection here. Then I can call it as top and then press enter. So everything is now ready. Left, right, bottom, and top are our boundary condition, the surface. So I can now close the SpaceClaim. I don't need to save it, as you know. You can just simply click on the save on the workbench. So everything will be saved inside in this project. So geometry has been done. Without any delay, I will double click on the mesh and go to ANSYS Meshing. Okay, now we are in the ANSYS Meshing. You can check other previous sessions to see the details of the meshing. I will just go through the process. First of all, I need to define actually face meshing to have a quad mesh. So I will select, we are in the face selection. I will select this face, click here, apply. So it's a quad mesh. So I will go to add sizing, right click on the mesh, insert on the sizing. So in this case, as we are using the same setup for all edges, I can select, first I will change to the edge selection. I will select all of these edges by click here, hold the control key and select the other 4. So I will press on apply. Then I will change this element size to number of division, and then I will change number of division to 35. Okay, then I need to have one bias. So I will, and I'm just going to have the dense mesh here beside each valve. So I will select this option, and then instead of bias factor, I will use the smooth transition. I will keep the default value for this rating. So as you can see, we have a dense mesh here beside each walls. This wall, here also, and in the center we have a larger mesh. So now I can click on the mesh, right click, and then generate the mesh. And if I go to statistics, I can check the number of elements, 1225, number of all meshes here. Then finally, I will right click on the mesh and update. So this mesh will be transferred to the Fluent successfully to the workbench. Now I can close this ANSYS Meshing, then save the project, and now let's start the ANSYS Fluent by double clicking on the setup to open the ANSYS Fluent launcher. Then select double precision and select 4 processors as a solver, and then press on start. Okay, now we are in the ANSYS Fluent mode. This is a steady flow, as we know. We can also first check this size, number of mesh here. As you can see, it is the same as Fluent Meshing, 1225. Then we can do a perform mesh check and check the minimum volume. This is a positive value, so it's okay, and there is no error, so we can stop. So we will keep this value here. We'll close this window and go to the task page. So here we can start with the model. We need to activate the energy equation. So I will double click, press on energy equation, okay, and then as we discussed, this is a laminar because the Rayleigh number is roughly 1E6. You can calculate by yourself, but it's a laminar flow. So I will double click on the viscous model and then change the turbulence to laminar flow, and then simply press on OK. So we have done everything in the model. We can go to the material as we discussed. This is actually a Boussinesq equation for the density. And so we need to go to the material. We are working with the air, but different material actually here. So first of all, I will go to density and change the constant to Boussinesq. So we need to define density and also thermal expansion coefficient here. So to do so, actually, as we know, the temperature here is 0 degrees Celsius and here is 25.2. We will calculate based on these two. So our temperature reference is the average between these two temperatures, so it will be 285.75 Kelvin based on this value. The thermal expansion coefficient will be calculated, and it is 0.003496, And finally, reference density will be 1.2353. We will enter this value in the under the Boussinesq model. So I will write here 1.2353, and for the thermal expansion I will write as 0.000349996. Then I will press on create and change, and then close this window. For the Boussinesq model, we need to go also to the physics and do some changes here under operation condition. We need to activate gravity. Click here and then enter minus 9.81 meter per square second, and then we will use the temperature reference as we calculate 285.75. This is the value for operating temperature, 285.75 Kelvin. Just it should be on Kelvin, and then press on OK here. Then after that, as we have only one material for the fluid, so we don't need to go to the fluid, but I've just open it to see. We only have material air here, so we can just keep this default and close this window. Then I will go to the boundary condition. As we discussed, the top and bottom walls are adiabatic, so the heat flux here and here are 0. So I will open it. The default setting is adiabatic wall, so we don't need to do anything. Just open it to check. As you can see, thermal conditions is heat flux and 0 for the bottom wall. So I can close this window, open the top, and check. For the top wall also, I will go to thermal. It's a heat flux and the value is 0. So I just need to close this one. Then I will go to the left boundary condition here. So for the thermal tab, I'm going to change this heat flux to the constant temperature. So it is 0 Kelvin, so it will be 273.15. Then I will press on apply and close this window, and then right click on the right wall boundary condition to open it. Go to the thermal. Again, change the boundary condition to temperature, constant temperature, and it is 25.2 degrees Celsius. It means that this would be 298.35 Kelvin. So I can simply press and apply, and then close this window. If you are going to work in the Celsius unit, so you can just simply go to the domain here, select units, and press here on one of these qualities, and then on the keyboard press on T, select again temperature. So you can simply change this unit to Celsius, so you will see it will automatically switch between different units. But I'm going to work with Kelvin, so I will close this one, press and apply, and then close this boundary condition. After that, I will go to the method. So here, very important to select the correct methods for the pressure velocity coupling. The coupled is suitable for this problem. I will keep it as it is. Second order for momentum and energy, but for the pressure, it is better to select presto for this natural convection problem. So that's it for this one. And for the control and the under relaxation factors, I will keep the default value here, and then I will go to the monitor and double click on the residual. I need a very low residual. I can change this value, but I will keep this default because I'm going to untick this check convergence. It means that I will give a number of iteration 250, and it is enough for this problem. And so if the residual reach to this value, it will continue to reduce the values until it reach to 250 iterations. So I will press on OK here, Also, I can go to physics, and for reference value, I can change this value. The area for 2D problem in this case will be the same as the length. Then length will be 0.07 meter. Density is reference density 2353 as we calculated before. And for the temperature, we will put reference value 285.75, and then I will keep the other default value. Then finally I can go to initialize, but I think it's better before that to go to custom field function. I can do this one in the post-processing stage, but I can also define the Nusselt value here. Actually, Fluent reports wall heat flux and temperature, but it doesn't directly compute local Nusselt number. To visualize how heat transfer varies along the walls, for example, Nusselt versus wall position, we need to compute it from our custom field function. So to do so, I need a definition for local Nusselt number. This is local Nusselt expression. As you can see here, I can define this equation into our custom field function as like this one. This is the length of a square, and this is the conductivity, as you can see here, and this is temperature difference between right and left walls. And we will define this heat flux from the Fluent. Okay, so to define this expression, I will go to the user define, and under field function I will select the custom field function calculator. So here we have a minus sign, so I will press on minus. So now I need to heat flux, so I will go to field function. Under the wall fluxes, I can search for the total surface heat flux, which is this one. So I will press on select here. So we have heat flux here, and it will be multiplied by 0.07 meter, the length. It will be divided, and then I will open the parentheses here, and then I will input this thermal conductivity 0.0242. It will be multiplied by, and then open parentheses again, 298.35 minus 273.15. So we'll use and close the parentheses again, and finally I will call this function as Nusselt local or local Nusselt number, and then press on the define. Finally, I can close this window, so we can check again. Heat minus heat flux multiplied by 0.07 divided by this value, conductivity multiplied by temperature differences. So I will close this one, and then go again to the Fluent. Finally, I can go to initialize, use hybrid initialization, press on initialize, and then go to run calculation, change this value to 250, and then finally press on calculate. So you will see the residual for different equations are going to be converged, and as you can see, there are mostly under the defined value E-3, because I asked Fluent to go until 250 number of iteration. You can also continue this value by pressing again, but I think this value are enough for this part. In this stage, I will go again back to Fluent Workbench and press on the save button to save ANSYS Workbench, and then switch back to Fluent to go to check the results. First of all, we can start with the graphics here, and the velocity vector, for example, double click on it. I can call it as vector velocity, and then here First of all, I will select draw mesh and deselect the domain, just the boundaries, and then press on display. After that, I will select the velocity, and under that I will go and select the y velocity and then press on display. I can decrease the size to, for example, 0.5, display again. So you will see the pattern of the fluid here. The flow, it's I mean, you can see the circulation inside this cavity. So I can decrease the size to have a better visualization for the velocity vector, its y velocity. So this is the hot wall here, and this is the cold wall. So here the air will be rise, go up, and then coming down, and there is a circulation here, as you can see. Now I can close this window. Now I can go to contours, double click on it. I can create a streamline contour. I will call it contour streamline, and then under velocity I can select the stream functions, as you can see here, and then press on display. Here also you can draw the mesh and then save and display again. You can change some settings here. For example, you can uncheck the field part and use banded value, for example, here, and there is and this is the streamline for actually the contour for streamlines. You can also double click again on the contour and use select the contour pressure. So we should go to the pressure and the static pressure, and then display. Here you can see a contour of pressure also here, but I'm going to change this one to contour of temperature. So under contour off, I will select the temperature, static temperature, and display again. I can uncheck the field value, and then you will see the contour temperature. Here the unit, the value is 273, and here 298. I can go to the unit and change this temperature to Celsius here, and then save and display again. So it will be changed to Celsius, as you can see here. Okay, now I'm going to create two plots, one for the y velocity in the center line here. First of all, I will display the geometry. So I'm going to create one line here and then plot y velocity on this line. So to do so, I will go to the results and create one line ray. I need to define a start and end point. The start point is here, x is 0 and y is 0.035, the center. I will copy this value, paste it here, and then change the x value to 0.07 for the end point here. So I can just call it as y 0.035 and then create this line. And close this window, display again, select the line, and you can see I have this line. So now I can go to the XY plot, double click on it, y velocity plot, and then the x-axis will be the position for the plot. So I will keep position on x-axis. Here I will select velocity, and under that I will select the y velocity, select the line, the newly created line, and then keep this plot direction, because the value of the y velocity is on this line and the x direction. So now I can press on save and plot, and as you can see, the y velocity is changing like this under that center line on y 0.035, and actually this is the x position. So you will see the variation of the y velocity on this line. So here beside the hot wall, the velocity will be increased, and here it's a minus value. It means that the flow is going downward like this, and it's a circulation in the square. So that's it for this plot. I can close this window, right click and select another plot. This time I'm going to create a plot for the Nusselt number, local Nusselt number that we have selected. So here I will select custom field function and I have Nusselt number, and this Nusselt number actually will be I will plot it for the left wall. So here I will select the left wall here. As you can see, again I will keep the position on x axis. So the coordination will be on the x axis, and for the y axis I have this Nusselt number, but because I select the left wall, it's a vertical line, so the plot direction will be on the y direction, so it's 0 and 1. Now I can call it as local Nusselt or Nusselt local like this, and then press on save and plot, as you can see here. And this is the variation from bottom to top side of our square, and here as you can see it is roughly 18, the Nusselt number for the top side of this wall, left wall actually, and at the bottom it is roughly 1. Nusselt number is 1. So now I can go and create a report from surface integral. I will select the area weighted average because I'm working on one wall, left wall. So I will select left wall, and I'm going to get an average for this Nusselt number. So I can press on compute, and I will have this value as 8.97 for the average value of the Nusselt number. If we compare this value with some references, if we compare this value with one reference, so the predicted average Nusselt number is compared with benchmark solution of this reference, the Walt Davis, is very well. So for this Riley E1 E6 and Prandtl of 0.71, this reference obtain a value of average Nusselt number of 8.79a for fine mesh. But for this tutorial, with this coarse mesh of 35 multiplied by 35 number of mesh, we found this number as 8.9777. So you can change this mesh number and generate the new mesh and compare with the results for the finer mesh actually. So now I can close this windows and then save again the project, as you can see here, based on this value with the workbench. Now we can close this session also. We can work on another natural convection in the next lesson. So please follow us. And so that is all for this actually tutorial. So thanks for watching, and see you in the next lesson.